Okay, starting the next problem below. I do also want to point out one more thing is that if we look at these forces to push these guys together, notice that like it's not creating any torque. If this force was maybe like acting along the edge of the disk, that would be creating a torque, right? Adding more angular momentum into the system. But in this case, we're just pushing them together, and notice that this force is like 180 degrees. Well, yeah, it's acting, if you try to look at this guy and see what kind of torque it creates, it's not creating any rotation, okay? It's the radial direction it is away from the center is 0, so the radius is equal to 0 if I do the torque equation, right? RF sine of theta. So R is equal to 0, so this one's creating no torque. It's basically acting through the center line of rotation. Okay, so that's how we know that we can conserve our angular momentum here. We have conservation. Okay, so let's see what's going on here. Okay, so we have a cylinder with a moment of inertia I. So this first guy has a moment of inertia. So this guy rotates about a vertical frictionless axle with an angular speed Wi. A second cylinder, this one having moment of inertia I2 and initially not rotating, drops onto the first cylinder. Because of friction between the two surfaces, eventually they reach the same angular speed at Wf. Calculate Wf, show that the kinetic energy of the system decreases in this interaction, and calculate the ratio of the final initial rotation energy. Okay, so this whole thing is spinning, this rod plus this guy here, this I2 just sort of falls down, and then they are stuck together, and slowly friction gets this guy up to speed with the bottom one. Okay, so let's look at how we would model our equations. Okay, all right. So we don't have any forces here that would be acting to cause any kind of a torque, right? Nothing that's gonna cause anything or gonna cause a change, right? We know that torque, right? Delta T is equal to the change in angular momentum from the way that we introduced our equations. So we don't have that happening here, right? We don't have a, sorry, the torque, I don't know why. So this would be like your force, and then your torque actually would be like going up in this kind of direction here. Sorry, so the first thing that I wrote was not correct. So we don't have a force that's changing that system. Okay, torque is equal to RF sine theta, right? So we don't have a torque that's going to change our angular momentum, and we have conservation. Okay, so we're going to do, we have the initial angular momentum is equal to the final angular momentum. We know that our initial angular momentum, the expression, we have I initial, right? Mass moment of inertia initial times angular velocity initial, and then the final is equal to mass moment of inertia final times the final angular velocity. Okay, so what are those things, right? Well, so let's see here. So for the first system, we have Li is equal to the initial, and then we don't have any, so from what we saw up here, right, we were adding them together, right? If we think about like, right, L1, right, plus L2 is equal to I1, right, plus I2 times some shared W, right? Because there we have an inelastic collision here. So we know that the angular momentum of the first disk at the very beginning is 0. This is not spinning at all in the beginning, so we know that L2 is equal to 0 at the beginning, but then at the end they do have some shared angular momentum, okay? So this is our initial, so we're going to set this guy, this is our initial value, okay? So this plus 0, right, for L2, because it's not rotating in the beginning. And then for LF value for this one, we have these guys, right? I1 plus I2, right? Times some shared WF, okay? So IF is equal to I1 plus I2, right? So we're gonna plug that in. Okay, cool. So let's say I1 WI. Okay, so let's set these guys equal. So we have Li equals Lf. So we have I1 Wi, right, is equal to I1 plus I2 times WF. And in this case, they're asking us to solve for WF. So our expression is WF is going to be equal to, if we just divide this term. So I just moved this over. Well, actually, maybe I'll leave it on the same side because I don't want to be more confusing. I1 WI from this side, right, just divided by I1 plus I2 is equal to WF. Feel free to put me on like double speed also too if I'm talking a little bit too slow through this one. Okay, so that's the expression for our final angular velocity here. Okay, so that's what it asks us, calculate WF. So it doesn't give us any value, so this is just an expression. So this is our solution for part A, just the variables. Okay, what about part B? Show that the kinetic energy of the system decreases in this interaction and calculate the ratio of the final and initial. Okay, all right, for part B. So what happens to our kinetic energy? Okay, let's think about our equations. We have 1/2. So for the initial kinetic energy, so K, E, I, we have 1/2 I1 WI squared. And then KEF is equal to 1/2 IF, right, WF squared. Okay, so a very important takeaway here is that in inelastic collisions, and we just saw this before, but in inelastic collisions, that the kinetic energy, KE, is not conserved, meaning that there will be a change, basically. So momentum is conserved, but the kinetic energy itself is not conserved. Okay, so we can't set initial equal to final. That's what we're seeing here, right? We can't say the initial kinetic energy is equal to the final kinetic energy because there's going to be some change here. Just the momentums are equal. Okay. Okay, so we're trying to find the ratio. So KEF over KEI. So what we end up with at the end, right? So 1/2 IF WF squared, right, divided by 1/2 II, or I1 WI squared. And if we kind of plug in what we have for those terms, we can simplify things a little bit. So we're going to end up with 1/2, and this is I1 plus I2, right? WF squared divided by 1/2 I1 WI squared. And we're going to be doing some algebra here because we have this WF term, we found it. So we're going to be plugging it in. So let's see what else we can cancel from this expression. We can cancel out our 1/2s, right? So we can cancel out this. This is just turning into an algebra problem. Feel free to skip ahead if you would like. Okay, so we're going to just find this in terms of, okay, so then we have, for WF, we have I1 WI, right, over I1 plus I2. Okay, and I'm just plugging this in for my WF value. So this whole thing is going to be squared. And then I have I1 plus I2, right, divided by I1 WI squared. Okay, so I end up with, if I think about pulling out this WI term, so from this step to the next one, let's stop screwing around here. Okay. Okay. Then I can pull out, so I1 plus I2, right, these guys, and then I have I1 WI, right, divided by I1 plus I2. And then I'm pulling out this, and this is still squared. I'm going to pull out this WI squared because I noticed that I have it in my denominator as well. So WI squared, and then I can cancel these guys, right? Cancel them. And then I also have this guy squared. So let's see here, WI. Am I losing a term here? to 1/2. So my final answer here, I'm going to let you guys go through the rest of the algebra. Actually, I'm going to pause 1 second because I think I have a mistake. I'm just going to backtrack, but I don't want to waste your time on the video.